Hiya. So in this video, we're going to talk about multiplication moments. Uh, so what this idea is kind of starting from is, remember, well, I guess now like thousands of weeks ago, we talked about functions. So one of the strengths of random variables was that we can kind of put in functions, right? So instead of just looking at, like, we could make y equal to f of x, right? Or something like that. That, like, this was a fairly strong thing. The examples we gave though weren't that great. It was kind of like, man, like, who cares? Like, I think a lot of people were like, what? Like, we don't get it. Like, what? Who cares, right? Um, and this is where we'll actually start seeing where this is actually viable and why it's a good thing. So first off, what we're going to do is look at the expected value. So let's first calculate. So if we're going to first set y equal to f of x, just like before. And we're going to look at the expected value of y. So here, the normal definition is that we take all y. So we get y times probability that y is equal to y. And then what we're going to do is we're going to plug in our function. So here what we're doing is we're switching the y's to x's. So we're going to look at all x. Here we have f of x, right? Y is equal to f of x. P of f of y equal to f of x. And maybe I should put this. It's going to do all of it. Why is it doing all of it? I just want this part. There we go. Oh, but my thing is there. Well, we're just gonna, here, I'll put it underneath. I'm out of room. Why did I do this? So here, I'll put this here. E of y is equal to. So we get this function here, right? So we have p of, why is this? Oh, because there we go. So here we have, this is wrong. So we have p of f of x is equal to f of little x. And that's the probability. But notice how here we can just take the inverses, right? So if I were to take, so if I have f of x equal to f of little x, then I can take the inverse of both sides, minus 1, and I get x equal to x, right? So what we end up getting is the following, which is probably a little weird. So this is equal to, I'll make this a little higher up, f of x times p of x equal to x. So in other words, if y is a function of x, so here you can kind of think of this as e of f of x. What we're basically saying is this function we can put in front, and then the rest we can forget about. We don't care about what's inside the probability. We just look at all the x's. So that's actually pretty strong. What this is basically saying is, like, so say if I have some function f of x, x to the k, right? Like, that's just what my function is. If I look at the expected value of x, like capital X to the k, well, this is just, I take the summation of all of x. I have x to the k, so I do x to the k, and then I just leave my normal probability. That's it. Like, that's pretty cool. Like, we don't have to worry about calculating the function inside the probability function itself. We just multiply by this thing. And this is actually known, so these x to the k is known as the kth moment of x. This has to do with some function called the moment function. Don't worry about it too much. But basically some like terminology, if k is equal to 1, then it's called the first moment, 1 first. K is equal to 2, we have the second moment. The first moment, I guess I should say, is normally called the expected value. So notice how x, we get x to the 1. So it's just the expected value. I should write that down. So expected value. The second moment is normally called the mean square. So this personally makes me think of like some little super angry square, like just like angry, like I don't even know. Let's so we have like some square here and it's angry. Angry. I don't even know how to draw angry. We'll have a little fist for angry fist. Grr. That looks angry. That looks angry enough. Angry square. So like k is equal to 2 gives us the mean square. Like it looks like they're gonna beat you up. Anyway, what time? Yeah. So what we'll do is we'll kind of keep going and looking at an example of this to kind of see how this works. So let's look at the mean square of the discrete uniform distribution. So let's look at example 28.1. And so in this case, what we have is we're trying to calculate the mean square of the discrete uniform distribution on the set 0, 1, 2. So first let's do e to the x, right? Just to kind of lay down the groundwork. So this is going to be the sum of x is equal to 0 to 2, right? Because we have 0, 1, 2. So x, 0, 1, 2. And we do x times x is equal to x. So we have 0 times, the probability here is given by this definition, right? So we're told discrete uniform. So everything has the same probability because uniform. And since there's 3 options, there's going to, the probability is 1/3, right? So we have 1/3. So plus 1 times 1/3 plus 2 times 1/3. So here we have 1/3 plus 2/3, which is just equal to 1. Okay, so this is the normal square, the normal expected value. This is the first moment. How about the second moment? So the mean square. It's basically the same thing, except we square the number in front. So we get 0 squared times 1/3 plus 1 squared times 1/3 plus 2 squared times 1/3. So this is just 1/3 plus 4/3, which is equal to 5/3. Now this brings up a super important point, and that is that e of that we never have this, right? So we can never switch e and f. So the expected value of the function is different than the function of the expected value, and we see that in the thing above, right? So this. I guess this has tiny room here. So I'm going to write this over here. We have the expected value of x squared is equal to 5/3. But the expected value of x squared is equal to 1 squared, which is 1. These two are not equal to one another. So this is something to note. Also, this is something to note about the way I write things. Notice where the square is. E to the x squared is not equal to e to the x squared. And this is not equal to e squared x. These all mean 2 different things. So what do each of these things mean? And this is something that a lot of algebra teachers get wrong because they use all these different notations and it's technically wrong and it's really bad. This means e to the x times x. This means e to the x times e to the x, or e of x. And this means e of x. So each one is basically telling me different things, right? And so this is something to note, that these are not always the same. And notation is very, very, very important. So please note these things when you're doing things. And so we will stop this part here because it's been 10 minutes. And then I'll go into the linearity information in the next video. So I will see you then.